Next, a definition 1.7, interior points and the interior of a set. Before we look at the definition formally, let's take a look at a picture. X is a metric space with metric D, and Y is a subset of X. Now let's take a look at a few points of X: A, B, C, and D. D on the far right there is not a point of Y, therefore not an interior point of Y, whatever that means, since we haven't defined it yet. B and C visually, intuitively seem like they are interior points of Y, whatever that means. And A, which sits on the boundary of Y, is probably not an interior point of Y. How can we make our intuitive notion more precise? By an appeal to open balls. If we draw open balls around the points, then it seems to me that we get a mechanism for defining interiority. The open balls around B and C are, we can draw open balls around B and C which are completely contained inside Y, but not the case for A. No matter how small radius an open ball we draw around A, point A, we will always capture some element of X that is not in Y. So formally, if Y is a subset of a metric space X, then little x in capital X is an interior point of Y if there exists a positive real R such that the open ball centered at X of radius R is a subset of Y. And the set of all interior points of Y is its interior, denoted with Y circle. Next, a mini claim. A set contains its interior, meaning the interior of a set is its subset. And this follows pretty much straightforward from the definition. We are to show that if little y is an element of the interior of Y, then little y is also an element of Y. Well, let's look at the definition of an interior point. Since Y is an interior point, there exists an open ball centered at Y with radius R, such a R exists, such that the open ball centered at Y of radius R is a subset of Y. So little y is an element of the open ball centered at little y and radius R because the distance from Y to itself is 0, and this open ball is a subset of Y. Therefore, little y is an element of capital Y. And so we have established inclusion, and therefore the interior of a set is a subset of the set itself. Another definition 1.9, open set. This notion, the notion of an open set, is crucial in mathematics, in analysis, in topology, in other areas. And in the fullness of time, we will have opportunity to examine its properties and its application. But in the meantime, let's look at its definition. If Y is a subset of X in a metric space XD, then Y is an open subset or open set of X if the interior of Y is equal to itself. We have already established by claim 1.8 that the interior of a set is its subset, meaning left inclusion we have gotten for free from claim 1.8. If additionally the right inclusion is true, then Y is an open set of X. Next, a simple application of the notion of open sets. Claim 1.10, open balls in a metric space XD are open sets of X. Let's take a look at a picture. Capital XD is a metric space with metric D, and little x is an element in capital X. And consider an open ball centered at X of radius R. We are to show that the open ball BXR is equal to its interior. Well, the left inclusion we have for free from the previous slide, claim 1.8. If now we can show that we have right inclusion, meaning that an element of the open ball is an interior point, then our job would be done. Well, consider such a point y belonging to the open ball. If we can construct an open ball centered at y, which is a subset of the open ball centered at x of radius r, then our job would be done. Since y belongs to the open ball centered at x of radius r, the distance from x to y is less than r by definition. Consider a quantity s equal to r minus dxy. Since r is greater than dxy, r minus dxy is greater than 0, and so s is a real positive. And now further consider uh, an open ball centered at y of radius s. If this open ball is to be a subset of the larger open ball centered at x of radius r, then any point in this open ball must be a point of the open ball centered at x of radius r. Consider such a point. Consider an arbitrary point t belonging to the open ball centered at y of radius s. The distance from x to t is less than the distance from x to y plus the distance from y to t by the triangle inequality. And if we now substitute the value s for distance from y to t, then our less than or equal to changes to a strictly less than, given the fact that s is greater than dyt, because any point of this smaller open ball must lie at a distance less than s from y. And now if we substitute the value for s is equal to r minus dxy, then and follow through with cancellations, we get the result that the distance from x to t is less than r, which means that the point t, which was chosen arbitrarily from the open ball centered at y of radius s, is also a point of the open ball centered at x of radius r. And thus, this smaller open ball is a subset of the larger open ball, which means that the point y is an interior point of the open ball centered at b of centered at x of radius r. And since y was chosen arbitrarily, we have established that the open ball is a subset of its interior, which is what we set out to do, the right inclusion in this equation here. So open balls are open sets. Next, the unions of open sets are open. If you have a family of open subsets of a metric space XD, then if you take the union of that family, then the resultant set is open. Let U alpha be a family of open subsets of metric space XD indexed by index set I, and let U be the union of that family. How do we show that U is open? Well, we can show U is open if each and every point of U is an interior point of U. And how do we show that? Well, if we can wrap an open ball around each point of U such that the open ball is a subset of U, then we would have shown that that point is an interior point of U. So let's take an arbitrary point x of U. Since x belongs to U, surely it belongs to one of the U alphas in the family, i.e., there exists an alpha in the index set I such that x belongs to U alpha. And what are these U alphas? They are open. So since U alpha is open, there exists a positive real number R such that the open ball centered at x of radius R is a subset of U alpha. But each of these U alphas are subsets of U because that's how U was constructed. And so we have this chain of inclusions. And by the transitive property of inclusion, the open ball centered at x of radius r is also a subset of U, which means that x is an interior point of U. And since x was chosen arbitrarily, then each and every point of U is an interior point of U, meaning that U is a subset of its interior. And since the interior of a set is its subset by an earlier claim, we have shown inclusion in both directions. And therefore, U is equal to its interior, and thus U is open. A word about the use of colors in this proof. Colors serve to break the monotony of white text, and if judiciously chosen, they can highlight the logic of the proof. And I hope that I've chosen the colored items judiciously here. Next, something a bit more ambitious, but without a corresponding increase in the difficulty of the proof. Open sets are unions of open balls, i.e. any open set is a union of open balls. Formally, a subset U of a metric space XD is open if and only if it is the union of open balls in X. This is a if and only if proof. So we have an only if part going forward and an if part going backward. NTS here means need to show. The if part is trivial and is already solved for us in claims 10 and 11. Let's take a brief, quick peek at claim 10. Open balls are open sets, which we have already shown. And if open balls are open sets, then the unions of open balls are the unions of open sets. And by claim 11, the unions of open balls are open. For the only if part, let U be open in X and let little x be an arbitrary point of U. Since U is open, there exists a positive real number Rx such that the open ball centered at X and of radius Rx is a subset of U. And this is true for each and every point of X. Each and every point of X, there is an open ball with an associated Rx such that that open ball is a subset of U. And if you take the union of all those open balls for each and every point of U, then that union is also a subset of U because each of the individual sets, open balls are subsets of U. And so in this next line here, what we have gotten is the right inclusion, that the union of all the open balls for each X in U is a subset of U. For the left inclusion in this final line, observe that any open ball centered at a point X of U contains X. Why? Because the distance from X to itself is 0. And so, since this union runs over each and every point of U, for each and every point of U, there is a open ball centered at that point. That open ball contains the point, and so since it runs over all X in U, we have that the left-hand side is a subset of the right-hand side. And since we have both left inclusion and right inclusion, we have equality. And thus, U is a union of open balls in X. Voila.